Hi everyone, I'm Jim White, and in this video we're going to delve into Ohm's law and some of the historical facts that led to him being able to make that law. The first component necessary to make an electric circuit is wire, and luckily for the early inventors in the field of electricity, wire did exist. Back as early as 2000 BC, there was gold and silver wire that has been found on jewelry from back in that time period. In the 1300s, some musical instruments used wire. It might have been brass or bronze wire, I'm not sure. And that was also used on harpsichords in the 1400s. There was a big development for harpsichords in the year 1580 when the first iron wire was used in harpsichords. Then when the piano came along in the 1700s, steel wire was actually used, and we have the term piano wire today. So we had wire for making circuits, and then in 1800, Volta invented the electric pile battery, and this was alternate pieces of copper and zinc separated by paper that had been soaked in brine. And for the first time, a continuous electric current could be generated. Up till then, most electrical experiments were done with static electricity. So with the advent of the electric pile battery, the early physicists called this potential here the electromotive force, and it could be varied by the number of plates in the battery. So because Volta invented the battery, the intensity of this EMF was designated the volt, and we use the symbol V for this today. Now in 1820, Oersted noticed that a current carrying conductor near a compass needle deflected that needle. And that gave the first time that there was a way of sort of indicating the intensity of an electric current. And that's where the letter I comes from in Ohm's law. Also in 1820, Ampere published his Amperes Force Law, and this has to do with the force between parallel conductors. And apparently back then they did discover that there were magnetic fields that caused conductors to either attract or repel depending on the directions of the currents. So this current intensity came to be measured in amperes, or just shortened to amps, and today we use the symbol A for that. Okay, here we see our first electric circuit, and we have our symbol here for a battery. The symbol kind of makes sense since the battery was a stack of metal plates. So that would be what these would indicate. And I believe this symbol came about as just representing a bunch of wire. So you can increase the length of wire with a zigzag like that. Today, this symbol is also a recognized symbol for a resistor. Now here's all the indicator letters that we've talked about. They called the potential of the battery the electromotive force, which was just abbreviated with the letter E. The magnitude of the EMF was given the term volts, and we use the letter V for that. The intensity of the current is represented by the letter I, and we measure that magnitude in amperes, which we abbreviate as amps, and we use the letter A. Now, the resistance of a circuit, the letter R was used to designate resistance, and to honor Ohm for Ohm's law. The unit of resistance is the ohm, and it's represented by the Greek letter omega. So Ohm's law is basically this: I equals E over R, or the magnitude of the current is proportional to the electromotive force divided by the resistance. And of course, that equation can be solved in two other ways. If you know E and I and want to find R, or if you know I and R and want to find E, they're all three, that's just three forms of the same equation. In 1841, James Prescott Joule came up with what's known as Jules Law, which shows the relationship between electrical power and current and resistance. This was the original form. And of course, this equation can be expressed two other ways. I'm guessing that what he might have done was to put a resistor in a known quantity of water and then see how varying the current changed the rate of change of temperature of the water. So the unit of power ended up being named for James Watt, and much earlier Watt had made major improvements to the steam engine. So back in those days, we had things going on with respect to mechanical power as well as electrical power. And we'll try and relate those two together here in a little bit. So the unit of power was the watt, and it turns out the unit of energy ended up being named after Joule. And the unit of energy is the watt second. So there's a certain amount of energy if you dissipate 1 watt for 1 second. That's 1 joule of energy. So it's a watt second. So that can also be expressed as a watt is a joule per second. Now your electric bill is in watt hours, so that's watts per unit time, so you're really paying for energy. So it's important that you thoroughly understand the difference between energy and power if you're going to go on in either of these fields. So we'll talk a little bit more about that, and I've included some links to some other videos that explain this more thoroughly. Okay, we've covered Ohm's law from a theory standpoint. Now let's look into some practical aspects of Ohm's law and Joule's law. Here's, you're probably familiar with batteries, and this battery is on the end of an electric drill. And here we can see the battery is rated in amp hours, 2.6 amp hours. Now, since the battery also has a voltage associated with it, we're really talking about the battery can supply power for a certain amount of time, and we know that's energy. So batteries are, in a roundabout way, rated by their energy. Now, that says 2.6 amp hours. That may be the point at which the battery voltage is 1/2 its initial value. That's common, at least with these kind of batteries. They're usually rated in milliamp hours, and the number of milliamp hours is usually when the voltage is quite a bit less than its original value. In the case of this battery, if you look at its data sheet, the milliamp hours is to 1/2 the original voltage. So most people are familiar with batteries, and most people are familiar with wire. Now, what we have laying here is bare wire. Back in the early days of electricity, and the physicists that were originally experimenting with electricity, all they had was bare wire. And then that prevents you from making coils of wire and things like that increase the magnetic fields and allow you to do things like make ammeters and so forth. So, well, it turns out that women's hats, the brims were held out by wire that was wrapped in silk. So the first wires that were insulated were wrapped with silk or cotton and then held in place with wax or paraffin. So we're fairly familiar with batteries and wires. These are bare wires. Most wires that you see normally are already insulated. And what about resistors? Well, here's a resistor you might be familiar with. This is a little electric heater, and you can see the wire in there in coils. And when this thing is powered up, the resistors get red hot and produce a lot of heat. Incandescent light bulbs are basically resistors. Then here's resistors that are commonly used in electrical and electronic circuits, and you may not be familiar with those type of resistors, so we'll talk more about those as we cover more of the practical aspects of the early electrical laws. Okay, what I would like to do next is demonstrate Ørsted's discovery of how a current conducting wire would deflect a compass needle. So here's a 1.5 volt battery and a piece of wire. And I think you can see the needle deflecting there. Now as I get the wire closer to the compass, you see a lot more deflection. And let's do it this way. You can see I'm a fair distance away here, and I think you can still see the deflection. Now notice that the red end of the needle is moving to the left, and if I reverse the battery, you can see the needle deflects to the right. So through that, I'm sure they realized that a current had a polarity. Now here's a AAA battery, and you can see even that small battery generates enough current to deflect the compass needle. Okay, I'm going to repeat our little experiment with the current carrying wire and a compass, and instead of a battery I'm going to use a power supply, and in that way I can vary the current and show in more detail what happens. Now, of course, the compass is pointing north, but I would like that needle lined up with the conductor to start with, and that gives us the maximum sensitivity. So I have a permanent magnet here that I'm going to turn to get that needle to line up there with the wire. Now, let's start out by setting the current on the bottom scale. We're on the low range here of current. So on the bottom scale, let's go to 0.2 amps. And we can see the needle has deflected slightly. Now I'm going to stay on the compass and go up to 0.4 amps. There, I think you saw the needle turn some more. There's our 0.4 amps. Next we'll go up to 0.8 amps. If you watch the needle, see it turned a little further. Now I'm going to double it again and go to 1.6 amps. And we can see that the deflection is not very linear, but at low currents it's pretty close to linear. It's just as we get more and more perpendicular to the wire, it takes more and more current to turn the needle anymore. So the next thing we could do is try to increase the sensitivity by putting more turns of wire around the compass. And to do that, we'll need to use insulated wire. So I'll change the setup here off camera and then we'll get back to it. Okay, here I've taken a piece of red insulated wire and wrapped it around the compass twice. Now, because there's conductors going this way on the top and they go around and back in the opposite direction on the bottom, having two turns like this should be the equivalent of 4 turns going across either on the top or the bottom. So I'm guessing the sensitivity will be about 4 times what it was before. So let's take our current up to our 0.2 amps. And I think that's more deflection than we had before. Now I'll take it up to 0.4 amps. And you can judge for yourself if that's more deflection than we had before. So by adding more turns, we should be able to get the this ammeter now even more sensitive. And I'm sure through a process like this that the true amp meter was developed. Here are 2 resistors that I salvaged from an old circuit, and they're both the same value, and the one on the right is showing it's 0.51 ohms and it's 5% accuracy. That means if you measure it with an accurate ohm meter, if you measure a bunch of them, they'll all be within 5% of the 0.51 ohms. Now this, I'm trying to look, there it is, 3 watts. So this resistor is rated to dissipate 3 watts if you put enough current through it. And most of these power resistors get really hot, and it is rare to ever use them at their full power rating. Now here, with the resistor on the left, I've scraped off the insulation, and you can actually see it's really a ribbon wound resistor. So it's basically a wire wound resistor, but instead of wire, it's actually a flat ribbon. So let me show you another resistor here. This one, I hope we can focus on this. Of course, it's upside down. Okay. There, I think we can see it. It's a 500 ohm resistor rated at 5 watts. And this one is a 1% resistor, meaning if you measure a batch of them, they'll all be within 1% of 500 ohms. Now I've broken one of these in half. And have a piece of paper in the back so that you can see there's actually very fine wire that was wrapped around a white ceramic core and then glazed to hold everything together. Now, I also want to show you that the wires on these resistors are magnetic, so they're steel, and the end caps, this is hard to do with one hand, but the actual end cap is also made of steel. It's magnetic. And because the leads are steel, they're stiff, and when you bend them, you can actually mount this in a circuit board so that it's not quite down against the circuit board, because at the full 5 watt rating, that will eventually scorch a printed circuit board. So if you actually use this at the full 5 watts, you would probably want to stand it off the circuit board at least a ½ inch. And you have to consider the radiation, the infrared radiation from power resistors that could affect sensitive circuits nearby. Here's some common type resistors. These are ½ watt carbon film resistors. They're a 5% accuracy tolerance, and there's a standard paper clip for size comparison. And here's a 1/4 watt 1% metal film resistor. Now, a metal film resistor is more temperature stable. It has a better temperature coefficient than the carbon type resistors. And over here we have surface mount resistors. Now, these are 1/8 of a watt, and they come on a tape that you peel back the film and pull out the resistor. And usually these have to be mounted on a circuit board, But if you really want to, you can solder wires on the end and use them in breadboard type applications. Now, why would you want to do that? Well, you can get these in a 0.1% tolerance, and they're fairly inexpensive, whereas resistors like this in a 0.1% tolerance would be very expensive. So next I'll show you where you can get some resistors to play with. If you want to experiment with resistors, you're going to need to get some. And I know that digikey.com has, they call them resistor kits, which are assortments of resistors. Okay, the least expensive resistor is the carbon type. And let's apply the filters here. And the 1 ohm to 1 megohm would give you plenty of values to play with. And let's say half watt and 5% would be a fairly inexpensive resistor assortment. Okay, here it is. It's about $17. And for that you get 365 resistors, half watt, 5%. And here's a list of the values in heaven only knows what order. I have no idea why they arrange things in that order. So I'll show you what you actually get on a sheet of paper next. Okay, here's the values in that resistor kit arranged in a better order. And basically, these are the values in the ohm column. Then 10 times this value would be in this column. It's the same value but 10 times. And then we have a column of 100 times and a column of 1,000 times, 10,000, 100,000, and there's your 1 megohm resistor. So in each of these columns you would have these values times a power of 10. Now, why these strange looking values? Well, if you research something called preferred numbers, you'll see there's ways to arrange values of something that comes in many sizes, such as wire gauges and sheet metal gauges and hardware, things like that. And that'll give you some insight as to how these numbers were originated. So that's what you would really get in that kit. You'd get 5 resistors of each of these values. So that would enable you to experiment with all kinds of different possibilities. Okay, let's test our knowledge of what we've learned so far with a little problem. Let's say we had these 3 resistors in series, a 10 ohm, a 4.7 ohm, and a 1 ohm, all rated at 1/2 watt. What's the maximum voltage we can safely apply to those resistors without damaging any of them? We learned that the power dissipated by a resistor is the current squared times the resistance. Now, the same current would be flowing through all 3 of these resistors. So in the 1 ohm resistor, the current squared would be a ½ watt divided by the 1 ohm, or 0.5. The square root of 0.5 is 0.707. So we could safely have 0.707 amps flowing through the 1 ohm resistor. Now the 4.7 ohm resistor, the current squared would be the 0.5 watt divided by the 4.7 ohms, and the square root of the 0.106 is 0.326 amps. So we could safely have 0.3 amps going through the 4.7 ohm resistor. Now notice that's about half the current that the 1 ohm resistor could handle. Now the 10 ohm resistor could only handle about 0.224 amps. So we know then that that's the maximum current we can have. So if we solve for the maximum voltage, or the electromotive force, E equals IR, we get 3.52 volts. And that, of course, is limited by the 10 ohm resistor, since it will dissipate the most power at any given current level. So let's hook up some resistors and see what happens. Okay, here we have our 3 resistors connected in series, hooked up to our power supply, and with a voltmeter also attached so we can see the voltage across the network. Now the 10 ohm resistor is the one on the right. Now I'm going to go up to the 3.5 volts roughly. Okay, there's a little over 3.5 volts, and everything would be fine for a long time. But as you overload a resistor, its lifespan goes down. So let's take the voltage up further and see what happens. Okay, there's a little over 7 volts. So again, we don't see anything major happening right away, but I'm sure the 10 ohm resistor is way above its temperature rating for continuous service. And to make things happen quickly, we'll take the voltage up some more. Okay, we can see the 10 ohm resistor doesn't like that very much, and it's starting to smoke. And of course we're applying too much power to the 4.7 ohm as well, but it's not overloaded nearly as much as the 10 ohm resistor. And here I hope you can see the 10 ohm resistor starting to glow red. And the 4.7 ohm resistor's turning black, and the 1 ohm resistor is doing just fine at these levels. Now our current has gone to 0, so the 10 ohm resistor must be an open circuit at this point. So there's a demonstration of putting resistors in series. You can add up the resistances of each individual resistor to determine the total circuit current, but you have to be careful of the wattage, that you don't exceed the wattage of any of the resistors. So next, let's look at parallel circuits. Okay, let's look at resistors in parallel. Now, one variation of Joule's power equation is power is the voltage squared divided by the resistance. So from that, for a given voltage, the smaller the value of resistance, the more power would be dissipated. So here I'm showing a 10 ohm, 47 ohm, and 100 ohm, all half-watt resistors. So it looks like the 10 ohm resistor is going to be dissipating the most power when voltage is applied. Okay, here's our three resistors, 10 ohm on the left, 47 ohm in the middle, 100 ohm on the right. And I'm just going to crank up the voltage until one of them smokes. There's 5 volts. There's 10 volts. And you can see the one on the left is beginning to smoke there. And there's the red glow and fire. Well, we've seen that when we have resistors in series, we just add up the resistances to get the equivalent resistance. But it's a little more complicated with resistors in parallel. Now, if you have multiple resistors of the same value in parallel, you just divide by the number of resistors to find the equivalent resistance. But when the resistances are not equal, it becomes a little more difficult. So we need an equation to calculate the equivalent resistance of multiple resistors in parallel. So if we say the current going through R1 is I1, etc., we know that I equals E over R, so we have this equivalent for the three currents, and the total current, which would be flowing through the equivalent resistor, is the sum of I1, I2, and I3. So our new equivalent resistance is E over I, and I is this. And if we divide the top by E and the bottom by E, we end up with this as the equation for resistors in parallel. Now for the value of resistors shown here, we know that the maximum voltage is limited by the lowest ohm resistor. And for that 40 ohm resistor, if it's a half watt, we can only apply 4.47 volts to the circuit. Now the equivalent resistance for the three values shown is 18.2 ohms. And you really aren't going to find a 18.2 ohm resistor. The closest standard value would be 18 ohms for the 5% resistors. So the power into an 18 ohm resistor at 4.47 volts is 1.11 watts. So you can't replace the 3 resistors here with a half-watt resistor, nor do resistors come in any old wattage rating that you want. The next standard size in carbon resistors, 5% tolerance, is 2 watts. So actually, 3 half-watt resistors in parallel may be cheaper than a 2-watt resistor. So there's a lot of considerations when you're trying to simplify a circuit. Now there's a special case when there's only 2 resistors where the equation comes out very simple. And we'll look at that next. Now, my experience has been that it's very rare that you need to calculate an equivalent resistance of more than 2 resistors in parallel. So, going about it the same way as with 3 resistors, we end up with this equation. And if we multiply both the top and the bottom by R1, we end up with this equation. And then if we multiply through by R2, we end up with this equation, which is just the product of the resistances divided by the sum. So it's easy to calculate. There's no intermediate steps, and it makes things very simple. Now, if you had 3 resistors in parallel, you could use the product over the sum to get the resistance of the first 2, and then do that again with the 3rd resistor. So this is a very handy formula to have available to you when calculating resistances to solve circuits, etc. The electrical component that's most often just taken for granted is wire. And there's a lot to wire. We have bare wire and insulated wire. And the current carrying capacity of wire has a lot to do with the insulation on it. There's different insulation thicknesses for different voltages. Common standard voltages are 150 volt, 300 volt, and 600 volt. There's special colors. This type of wire is usually used as a ground wire. The green-yellow designates grounding both in building wiring and in electrical enclosures. Then here's bare copper wire that's also used for grounding. Bare copper wire tends to tarnish over time, which makes it difficult to make connections to it. So bare wire is often tin-plated, and sometimes that's referred to as bus wire. Then there's something called magnet wire, and it looks like this. Now that's not bare copper, that's insulated with enamel. And there's a piece here that I've stripped the insulation off the end. I hope you can see the change in color there. and I stripped that by scraping it with a knife so that I could make an electrical connection to that. Now this type of wire is used in making electromagnets, so it's referred to as magnet wire. It's also used in motor windings and transformers. So you have to think about wire when you get into circuits for real. Now here's a coil of number 30 magnet wire on a plastic bobbin, and I have it hooked up to an ohm meter here, and it's showing 4.5 ohms. Now if I were to pass 1 amp through that coil of wire, it would dissipate 4.5 watts, so it would get quite hot. When you have a lot of wire concentrated in a small place, it can get very hot from the heat accumulated from many, many passes of the wire. Now I'm going to hold this bobbin in my hand, and the heat of my hand is increasing the resistance of the wire. Copper has a temperature coefficient of roughly 0.4% per degree C. Now I'm going to dip that coil in ice water and you can see the resistance going down. Because it has a fair amount of mass, it's going to take a while for it to reach a final value. Now at 0.4% per degree C, if we go from 0 degrees C to 100 degrees C, you're going to see about a 40% change. So you can make a pretty nice and accurate thermometer with a lot of copper wire. Well, we're near the end now, and here's a summary of what we've covered. We've covered Ohm's law in 3 different forms. I would suggest just memorizing one of them. You can easily derive the other 2 whenever you need them, and that way it's easier to just remember one thing. Then Jules Laws, and there's 3 forms of that, and the easiest one of those to remember is power equals current times voltage, or pi, and you can substitute one of these in there to get resistance into the formula. And we showed that resistors in series, they just add up for the total resistance. And resistors in parallel, we have that formula, and it's good for any number of resistors. I found you rarely ever need to calculate more than 2 resistors in parallel at a time. And so that's this formula, which is the product of the resistances over the sum. Now, the next video, we're going to cover Kirchhoff's voltage and current laws, the superposition theorem, the Thevenin equivalent and Norton equivalent, and there's lots of laws to go here to have a full understanding of DC circuits. So don't miss that. Subscribe and get notified when the video comes out. Thanks.